Chapter 5.3 is called the integral test. So it reads, suppose the sum from n equals 1 to infinity of an is a series with positive terms an. So non-negative, not zero. Suppose there exists a function f and a positive integer capital N such that the following three conditions are satisfied. So we have to know, number one, f is continuous. Number two, f is decreasing. And number three, f of n equals an for all integers after that point, capital N. So any little n value after capital N. Then this gives us this formula down here, which is our series of an and the integral from whatever that capital N is all the way to infinity, f of x dx, either both converge or both diverge. Now, they don't necessarily have to converge to the same number, but if one of them converges, the other one will converge. So basically, we're using the integral to try to determine whether or not the series does. And they give you a couple examples over here via the figure 5.14. So in our first image here, part A, all of the rectangles are below the function, right? All right, so if we can inscribe rectangles inside the regions bounded by the curve y equals f of x and the x-axis, and the area bounded by these curves for x greater than or equal to 1 is finite, then the sum of the area of the rectangles is also finite. And in a similar manner, if you can make the rectangles, they say circumscribed, which means everything is outside of that. I mean, there is part of it within, but essentially both edges at the top will be touching or above the line. That's what that means. Then the region bounded by y equals f of x and the x-axis for x greater than or equal to 1, and the region has infinite area, then the sum of the area of the rectangles is also infinite. So basically, they either both converge or they both diverge. So let's try to take a look at these problems using the integral test. Use a couple from your book here. So we want to use the integral test here to determine whether or not problem 159 converges or diverges. All right, so let's take a look at this. So first of all, I'm going to take the integral from 1 to infinity. That's how we're going to look at it. We're using 1 to begin with. 1 over, it's a cube root of n plus 5 dx. Well, it's not n. We have to change that to x, don't we? So x plus 5. Because we're going to compare this integral to our sum. All right. So we're going to take a limit as we know as b goes to infinity. We'll use that of the integral from 1 to b. Okay. Now small b is what I use. Let's be consistent. Okay. So we can't evaluate by plugging in infinity. That's not going to work. But if we figure out the integral and use some actual tangible value, a variable b is going to work, then I can take a look at what's going to happen. All right, and that's going to be 1 over cube root of x plus 5 dx. So we're going to use a u substitution here. So u is going to equal x plus 5, and du is just dx. So let me scroll down. This is going to equal the limit as b goes to infinity with my u substitution, I plug in the u, so that's in the negative, it's 1/3, so it's going to be negative 1/3. So u to the negative 1/3 power du. Let's make that 3 a little more pronounced. Hopefully that's more visible. All right, so using the fundamental theorem from calculus, we can integrate this and evaluate. So this integral here, it's going to be 3/2 u to the 2/3. And then we replace the u with our actual value and evaluate it from 1 to b. So 3/2. Let's go with x plus 5. This quantity is squared, and it's cube root outside. And we're evaluating all this from 1 to b. So our limit, we'll leave the 3/2 out. And then we have it's like b plus 5 squared, and the cube root of that, minus cube root of, looks like 6 squared. Well, cube root of 6 squared is going to be a number. It's not, so 36, cube root of 36 is going to be whatever that's going to be, a little bigger than 3. But when we plug in our b as infinity, we still get, this still goes to infinity. So because that goes to infinity, this implies that our sequence or series diverges. Okay, well, there's a lot involved with that. Again, be careful of your notation. Notice I left the limit in there until, I guess I can do this. I just say this all equals infinity because this part goes to infinity. We're just subtracting off a constant. Doesn't matter. All right, so let's see if 160 is any easier here. So again, we're going to try to take limit. So there's our integral of 1 over x, ln of x, changing the n's to x's. Now that's going to be the limit as some b goes to infinity. We start at 2 because this is where we start here. So there's an issue. We're taking a natural log, so we can't have ln of 0 is undefined. Ln of 1 is 0, which would put that as 1 over 0, which would be a problem, which is why this one is starting at 2 and not at 1 or 0. And this goes to infinity, and this is going to be 1 over x ln of x dx. All right, so this is our limit. Here, we can let our u, let's go back to that same orange I used. We can let u equal ln of x, which means du is 1 over x dx. So this is going from, I guess, u to the negative 1 du. That works, right? Again, we can integrate this. So this is going to be limit as b approaches infinity. We're going to, well, u to the negative 1, that's going to be a natural log. So it's natural log of natural log. So this is ln of x, all evaluated from 2 to b. This equals limit as b goes to infinity of, we plug in the b first, so ln of b minus ln of 2. Now when we evaluate this, ln of 2 is going to be a number. It's not going to matter. However, ln of b is going to go to infinity, and if I take the natural log of infinity, will also be infinity, so it's infinity minus a number, which is just infinity. And again, by integral test, the series, what did I say series? Diverges. That's a couple examples of how to use the integral test.